Not just to a pile of facts, but to a profound understanding of how those facts connect, influence each other, and maybe even predict what might happen next, even when things are uncertain.
Hmm.
That's pretty much our mission today. We're diving into a topic that, well, fundamentally changed how AI deals with the beautiful, complex messiness of the real world.
Yeah.
Bayesian networks.
Indeed. And today's deep dive focuses on the groundbreaking work of Daphne Koller and Nir Friedman. They championed these things called probabilistic graphical models.
Right.
And their contributions didn't just add a new tool to AI's arsenal. They gave AI a sophisticated, mathematically grounded framework for reasoning under uncertainty.
Okay, so moving beyond just simple answers.
Exactly. This allowed AI to move beyond simple yes or no answers, or even just X causes Y statements, to truly understanding the maybe, the how likely, and crucially, the why.
Why? That's key.
It was a pivotal step, really, enabling AI to model the complex, nuanced realities of our world with unprecedented rigor and flexibility.
And what a revolution it was. Before this, AI often struggled when information was incomplete or ambiguous, which, let's be honest, is most of the real world, right?
Pretty much all of it, yeah.
So our goal for you today is to walk away well-informed about these, well, elegant graph structures, how they represent dependencies, and why they became absolutely critical in making AI more robust, more explainable, and fundamentally mathematically grounded. Get ready for some serious aha moments, because once you grasp how these networks operate, you'll start to recognize their influence everywhere in modern AI.
You really will.
From the way systems predict language to how they assist in critical, high-stakes decisions.
So when we talk about reasoning under uncertainty, what does that actually look like in the world of AI? I mean, how does a computer visualize or process maybe?
That's a great question.
Here's where it gets really interesting. Can you paint a picture of what these Bayesian networks are? Are they literal diagrams or, something more abstract hidden under the hood? Well, that's a great question because their visual nature is actually one of their core strengths. At their core, Bayesian networks, or belief networks as they're also known,
Belief networks. Okay.
are elegant graph structures that represent dependencies between variables in a system. Think of them quite literally as a visual language for probabilities.
Yeah, visual language. I like that.
Imagine a diagram. Each node or circle in the graph is a variable representing something we care about.
Like anything.
Pretty much anything. That could be anything from whether it's raining outside to a patient having a specific disease, a robot's location in a room, or even a particular word in a sentence.
Okay.
The directed edges, the arrows connecting these nodes, they represent probabilistic dependencies. They show how one variable directly influences the probability of another.
Influences the probability.
But crucially, not in a deterministic absolute way. It's not some hard-coded rule, but rather a statement of likelihood. This allows the system to account for the inherent messiness, the unpredictability, and the subtle nuances of real-world data where outcomes are rarely 100% certain.
So it's not just A causes B in a strict deterministic sense, like flipping a switch.
No, exactly.
It's more like A influences the probability of B. So if I see clouds, that increases the probability of rain, but doesn't guarantee it.
Precisely. That's a perfect analogy.
That's a huge shift from older, more rigid AI models, which often struggle with this kind of nuanced ambiguity, right?
So absolutely. They were often brittle.
It sounds like it brings AI much closer to how our own brains intuitively manage uncertainty.
Exactly. You've hit on a critical distinction. And to truly understand their architecture, we first need to consider their foundational skeleton.
Skeleton, okay.
The skeleton of a Bayesian network graph G over X, as Koller and Friedman describe it in their work, is essentially an undirected graph over X that contains an edge XY for every edge XY and G.
Okay. Unpack that a bit. Undirected first.
Right. What that means in simpler terms is that before we assign the specific direction of influence, before we decide if A influences B or B influences A, we first identify all the potential direct connections.
Okay. Just map out who's connected to whom.
Exactly. It's the underlying undirected structure that helps us visualize all the relationships between variables without initially worrying about the specific flow or direction of influence.
Like seeing the roads before you know which way is one way.
That's a good way to put it. Think of it like a blueprint of a building. It shows where all the rooms are connected, where walls might exist, before you decide which way the doors swing or how the electricity flows.
Gotcha.
This abstract view provides a clean way to see all the direct relationships at play, laying the groundwork for the more nuanced directional flow of probability later on.
That makes perfect sense. It's like seeing the entire road network before you decide which way the traffic flows on each street. Or maybe in biology, knowing two proteins interact before you figure out which one activates the other.
Precisely that kind of thing, yes.
But how do these abstract graphs actually help us solve real-world problems? Can you give us some concrete examples of how they're put to use, maybe in situations that change over time?
Yeah, definitely. And what's truly fascinating here is how these abstract graphs can be adapted to model concrete dynamic problems, especially those involving sequential data or hidden states,
Hmm.
things we can't directly observe.
Hidden states, like what?
Well, a classic example is representing a hidden Markov model as a belief network.
Hmm.
HMMs are used all over the place for sequences.
Right, I've heard of those.
And this is crucial for problems like smoothing. Imagine an agent has observed data up to a certain time, let's call it time k,
Okay.
but it wants to determine the most likely state at an earlier time, I, where I is less than k.
Ah, so looking back with new information.
Exactly. The goal, technically, is to find the probability PSIO0, okay, basically inferring a past state from a sequence of current and past observations.
So like in speech recognition, if a word was mumbled,
Perfect example. Imagine a speech recognition system listening to a noisy phone call. It hears a series of sounds.
Hmm.
Those are its observations.
right.
If a word was unclear a few seconds ago, the system can use all the subsequent words and context it has gathered since then to go back and refine its understanding of that earlier unclear word.
Wow.
The belief network helps piece together that historical puzzle by considering all subsequent phonetic and linguistic observations. It gives it the power to look backward and improve its understanding of the past based on what came later.
So it's about leveraging present and maybe even future-ish information to refine our understanding of something that happened previously, which might have been ambiguous at the time.
Precisely.
That sounds incredibly useful for many areas, like refining historical data or even in forensic analysis, where you're trying to reconstruct events from incomplete evidence, constantly updating your hypothesis.
That's the idea. You're constantly updating beliefs. And another powerful and very tangible application is in localization.
Localization, like
Wow.
finding where you are.
Exactly. Imagine a robot, maybe one navigating a warehouse or even a self-driving car, trying to determine its own position. This is the core problem of localization.
Okay, a big one for autonomous systems.
Huge. Poole and Mackworth's work shows a nice belief network representation of the localization problem. In this network, you'd have a variable, say loci, for each time step I, representing the robot's location at that specific moment.
Makes sense.
You'd also have a variable obsti for each time I, representing the robot's observation made at that time, data from its sensors like cameras, LiDAR, sonar, you name it.
Uh-huh.
And for each time I, there's a variable acti that represents the robot's action at that time, like moving forward or turning left.
Location, observation, action. Got it.
The network then allows the robot to continuously infer and update its current location based on this dynamic history of its sensory input and its own movements.
So it's constantly asking, given what I just saw and what I just did, where am I most likely now?
You got it. This is foundational in self-driving cars, for instance. The vehicle is constantly updating its belief about its position based on sensor data and its own movements. The Bayesian network is weighing the probabilities of different locations, given everything it has perceived and done.
Handling the noise. Sensors aren't perfect.
Exactly. Handling the inherent noise and uncertainty of real-world sensors in a really robust way.
So these aren't just abstract mathematical constructs, and they're like dynamic, living maps, constantly charting out how everything is connected and influencing each other probabilistically.
That's a great way to put it, living maps.
Especially for things that change over time, like a robot's journey or a hidden process in speech. It really makes them come to life, showing how they provide a flexible, powerful way for AI to perceive, understand, and navigate its environment under genuine uncertainty.
Precisely. And once we have these maps, once we've defined those nodes and the probabilistic arrows connecting them, the next crucial step is to understand how to read them.
Right, how to make sense of it all.
To truly unpack the intricate relationships they represent. And this leads us to a key concept: conditional independence.
Conditional independence, okay.
This is a cornerstone of understanding Bayesian networks. If we connect this to the bigger picture, it's about discerning which variables truly depend on each other and which are independent given certain information.
Given certain information, so the relationships can change based on what you know.
Exactly. This concept is absolutely critical for simplifying complex models and understanding their underlying structure. It's not just about listing connections, but understanding the hierarchy and flow of information, allowing us to ignore irrelevant data.
Conditional independence sounds a bit like saying, if I know this one specific thing, then a whole bunch of other things that previously seemed related suddenly aren't related anymore. Because the first thing tells me all I need to know, making the others redundant. Is that a fair way to think about it?
That's an excellent intuition, yes. That's pretty much the core idea.
It seems like a powerful way to prune irrelevant information and focus computational power where it actually matters.
It is. Think of it like a chain of communication.
Yeah.
If Alice tells Bob something, and Bob then tells Carol,
Well,
Carol's knowledge about that piece of information depends on Bob, right?
Mm.
But if Alice then directly tells Carol the same thing,
oh.
Carol's knowledge about the original source, Alice, might no longer depend on Bob. She has the direct information. Bob becomes irrelevant in that path.
Got it. Bypass the middleman.
Exactly. And a powerful tool for formally testing this is the D-separation criterion, developed by Collar and Friedman.
Key separation. Okay.
This criterion provides a simple graph-based algorithm to test for conditional independence, or I-equivalence, within the network structure itself.
An algorithm based on the graph.
Yes. Conceptually, for a probability distribution defined by the graph, conditional independence between two sets of nodes, let's say A and B, given a third set C,
Right.
holds if all possible paths that connect nodes in set A to nodes in set B pass through one or more nodes in set C.
Okay, so C has to be on every path between A and B.
Essentially, yes. And C has to block the path in a specific way defined by the rules of D separation. If these paths are blocked by the nodes in C, meaning C either intercepts the flow of information or makes the path irrelevant in some way, then A and B are conditionally independent given C. This graph-based test, which is actually simpler for the underlying undirected graph, makes it computationally tractable to check for these dependencies.
So you can just look at the map, essentially, and figure out dependencies.
Well, you run the algorithm on the map. But yes, it provides a formal visual method to determine if knowing the value of certain variables renders other variables irrelevant to each other, and that significantly streamlines inference and computation.
That's incredibly elegant. It's like the network has a built-in GPS that helps the AI efficiently identify and focus only on the truly relevant information, cutting through informational noise.
That's a nice analogy, yeah.
It provides a clear, visual way to identify what information is truly relevant to a specific variable and what can be ignored once certain conditions are met. This must be vital for keeping complex models computationally feasible and understandable.
Absolutely. And this naturally raises an important related question.
Yeah.
For any given variable in the network, what are the direct influences that truly matter? What's the minimum set of other variables you need to know about to understand this one?
Right, like its immediate neighborhood.
Exactly. This brings us to the Markov blanket of a node.
Markov blanket. Okay, sounds cozy.
Well, it's defined as the minimal set of nodes that renders the target node conditionally independent of all other nodes in the network. Once you know the state of the nodes in the Markov blanket,
You don't need to know anything else.
pretty much. For predicting that node, yes.
Yeah.
Essentially, the set of all nodes on which a variable's factor update depends corresponds to the Markov blanket of node xj.
Okay, and what's in that blanket?
This blanket comprises its parents, the nodes that directly influence it.
Its causes.
Its children, the nodes it directly influences.
Its effects.
And the co-parents of its children, so other nodes that also directly influence its children.
Okay. Parents, children, and children's other parents.
That's it. It's a local neighborhood that captures all relevant probabilistic information for that variable, simplifying calculations immensely by focusing only on the immediate context.
So you don't need to consider the entire, maybe huge network to understand one node's behavior or update its probability.
Correct. You just need to look at its Markov blanket.
So it's like saying, to predict or understand everything important about this variable, I only need to know its direct causes, its direct effects, and the other factors that also cause its direct effects. That dramatically reduces complexity.
Immensely, especially in very large networks, making calculations much more manageable and efficient.
Yeah, I can see that.
And one of the most significant advantages of Bayesian networks, And a key element of making AI truly explainable is their potential for a causal interpretation.
Causal. Okay, now we're talking about cause and effect.
Potentially, yes. By modeling relationships as directed graphs, BNs can help us understand not just correlations, that two things often happen together, but potential cause and effect relationships. This clarity is crucial for trust and understanding in AI decisions.
How so? How does the structure help with causality?
Well, the directed arrows inherently suggest a potential direction of influence. While correlation doesn't equal causation, the structure of a well-built Bayesian network often reflects underlying causal mechanisms. As Yoshua Bengio points out, understanding causal relationships is a major hurdle for AI breakthroughs.
Right.
Bayesian networks offer a powerful framework for this, allowing us to ask not just what is happening, but why an outcome occurred, and even what if we intervene.
What if questions, like simulations?
Exactly. What if we change this variable? How did that propagate through the network and affect the probability of other variables? This is vital in high-stakes applications, where knowing the root cause can lead to effective intervention rather than just prediction.
That helps move AI beyond being just a black box that spits out answers.
Absolutely. It moves towards a system that can provide justifications and insights, enhancing explainability.
That's a huge leap for AI. Moving beyond just X and Y happen together to X seems to cause Y fundamentally changes how we can interact with and trust AI systems.
It really does.
It allows us to ask what-if questions and predict the impact of interventions, not just observations. It's the difference between seeing smoke and knowing what started the fire, allowing for genuine problem solving.
Well put. However, building these optimal maps isn't always straightforward. There are challenges.
Okay, what kind of challenges?
Problems can arise in IMAP construction. That's building a map that perfectly captures all the independencies when dealing with situations like non-positive distribution.
Non-positive, like negative probabilities. That doesn't make sense.
Exactly. It can happen if the data or initial setup is mathematically problematic, or you can run into issues with deterministic relations between variables.
Meaning one variable always determines another, no maybe involved.
Right. If A is always equal to B, for example. Observing A tells you everything about B with 100% certainty. The network structure might struggle to represent this unique, rigid dependence clearly, leading to ambiguities and local independencies.
Because the framework is built for probabilities, not certainties.
Precisely. It can make it difficult to uniquely define the Markov blanket, and thus construct a perfect IMAP, an ideal network structure reflecting all the true independencies.
So you need good data and careful model design.
These situations highlight the need for careful data preprocessing and model design to avoid such ambiguities and ensure the network accurately reflects the underlying reality, probabilistic or otherwise.
So it's about more than just seeing connections. It's about understanding which connections are direct and which are merely circumstantial, and even hinting at the why behind them. That's incredibly powerful for explaining complex AI decisions.
It is.
But what happens when the map isn't perfect or the data is tricky, leading to these construction challenges? How do we then use these networks to actually get insights and make predictions? It sounds like the calculation part could get hairy.
Indeed, once we've constructed our network, maybe dealing with some of those challenges, the heart of using these networks is inference.
Inference, okay.
Which is the process of calculating probabilities of unknown variables given the evidence we have observed. This is where the mathematical grounding truly shines, allowing us to query the network and gain insights by propagating observed information through the graph.
Propagating information, like watching ripples spread.
Sort of, yeah. It's like having a complex system and wanting to know the likelihood of a specific component failing, given some initial symptoms you've observed. You update the probabilities based on the evidence.
Right. Once we've mapped out all these dependencies, using our belief networks or Bayesian networks, how do we actually reason and make predictions? It sounds like there's a lot of intricate calculation involved to figure out those probabilities, especially if we have many nodes.
There is, absolutely. But brilliant algorithms make it tractable. A foundational inference method, really central to Collar and Friedman's work, is the variable elimination algorithm.
Variable elimination. Sounds straightforward.
The key insight here is the ability to exchange summation and product. Let's break that down a bit. If you have a long chain of variables, say A, B, C, and D, influencing each other, and you want to find the probability of D, You typically have to sum over all possible combinations of A, B, and C. That number of combinations can grow exponentially. It gets huge fast.
Right, the curse of dimensionality.
Exactly. But with variable elimination, you can cleverly sum out each intermediate variable one by one, moving the summation inwards past the product signs in joint probability calculation.
Moving the summation inwards, how does that
Yeah.
help?
It means instead of having to compute every single joint probability over all variables, which can be astronomically large, this algorithm systematically eliminates variables by summing over their possible states at an earlier stage, essentially calculating intermediate results.
Ah, like calculating subtotals along the way.
That's a great way to think about it.
Yeah.
This systematic process avoids enumerating all possible states, which would be computationally prohibitive in larger networks, and significantly reduces the computational burden. It's an elegant factorization that dramatically speeds up the computation.
So it's a way of breaking down a massive complex calculation into a series of smaller, more manageable ones, rather than brute forcing every single possibility.
Precisely.
That's quite an elegant solution for efficiency, especially when dealing with many interdependent variables. It's almost like factoring out common terms in algebra to simplify a large equation.
That's a very apt comparison.
Mm-hmm.
However, even with variable elimination, for truly massive and complex real-world problems, imagine a network with thousands or even millions of variables. Even exact inference methods like variable elimination can still be too slow, consuming too much memory or time.
So what then? Give up.
No, that's where approximation methods become vital. They offer a pragmatic trade-off between perfect accuracy and computational speed.
Approximations. So not the exact answer.
Not necessarily the exact answer, but often extremely close and computationally feasible. One such powerful approach is cluster graph belief propagation, also from Kohler and Friedman.
Cluster graph belief propagation. Okay.
This method achieved approximation by relaxing the requirement of having a cluster tree, which is a structure sometimes used for exact inference and instead uses a set of pseudo-marginals.
Whoa, okay. Relaxing requirements, pseudo-marginals. Sounds complex.
Let's simplify. Sometimes, to perform exact inference, you need to group variables into very large clusters or cliques in the graph.
Right.
And that grouping itself can incur an exponential cost in terms of memory and running time. It just blows up. Cluster graph belief propagation avoids this by allowing a looser, more flexible structure and by using pseudo-marginals, essentially very good simplified estimates of those combined probabilities within the clusters to keep the system nimble.
Estimates. So it's guessing.
Not guessing randomly, it's making calculated approximations that are mathematically motivated. It allows for a less precise but far more scalable solution for huge data sets.
Okay, makes sense.
It makes it practical for real-world applications where perfect exactness isn't always feasible or even necessary within the time constraints.
So instead of demanding perfect exactness, it finds a good enough answer in a reasonable time frame, which is often exactly what's needed in practical AI applications, especially with big data.
You got it. It's about finding workable solutions when perfect ones are impossible or too costly.
Right. Are there other ways to approximate?
Yes, another powerful technique is variational variable elimination, again championed by Kohler and Friedman.
Variational, like finding variations.
Sort of. It involves optimization of the variational parameters. The algorithm essentially tries to find a simpler probability distribution that is as close as possible to the true complex distribution we're interested in.
Simpler but close.
Right. It produces symbolic expressions that are then optimized to find the best possible bound for the true partition function, a key quantity in these calculations.
So it's using optimization to find the best approximation?
Exactly. We're not just guessing, we're using rigorous mathematical optimization to get the tightest possible approximation to the true probabilities we can, given the constraints of this simpler distribution.
Okay, that sounds more principled than just guessing.
It is. Think of it like trying to fit the simplest possible shape, say, a cylinder, inside a very complex, irregularly shaped container. Variational methods aim to find the cylinder that best approximates a container's volume without needing to map every single nook and cranny.
Nice analogy.
This approach allows for efficient, large-scale inference, where exact methods would be intractable, by essentially interleaving variational approximation steps with exact elimination steps.
Combining approximation and exact steps.
Sometimes, yes. And what's fascinating is that many inference tasks, including a technique called clique tree calibration, can actually be viewed as optimization problems.
Ah, optimization again. It seems central.
It really is. For clique trees, Optimizing over the space of calibrated clique potentials directly leads to the exact posterior distribution. This optimization perspective is key to understanding the mathematical rigor behind these powerful methods. It transforms complex probability calculations into solvable optimization tasks.
So it sounds like Bayesian networks are not just about clever graph structures, but also about a deep mathematical foundation that leverages sophisticated optimization techniques to make these models practically useful.
Definitely.
Even in the face of immense complexity and the pervasive uncertainty inherent in real-world data, it's a marriage of elegant representation and smart computation.
That's a crucial point. And to ensure these complex models are robust and mathematically grounded, especially when data might be limited or noisy, another technique comes in: regularization.
Regularization. I've heard that term in machine learning.
Same principle here. Specifically, L1 and L2 regularization terms are often incorporated. These are essentially penalties added to the model's complexity during learning.
Penalties for being too complex.
Exactly. These penalties reduce or even eliminate multiple equivalent optima that can arise from redundant parameterizations. They push the parameters towards zero, promoting unique, simpler solutions.
How does that help?
Well, imagine you have very little data. Without regularization, a network might have infinitely many ways to set its probabilities that all yield a uniform distribution. It's essentially undecided because the data isn't strong enough.
Okay.
Regularization, by contrast, penalizes complexity. It nudges parameters towards zero and helps the learning process converge to a unique, simpler optimum, even with limited data. It prefers simpler explanations.
So regularization is like a guardrail, keeping the model from getting too complicated or unstable, especially when it doesn't have enough information to be perfectly confident.
That's a great way to put it. Yes, a guardrail.
It feels like a way to bake in a preference for simpler explanations, almost a scientific Occam's razor for AI.
Precisely. And crucially, this regularization leads to models with fewer edges and sparser potentials.
Fewer connections. Sparser.
Yes, because many parameters might be driven very close to zero, effectively removing weak connections. This sparsity simplifies the model, makes it more interpretable, and significantly reduces the computational load for inference later on.
Ah, so it helps with computation too.
Absolutely. It makes the networks potentially much more tractable to work with. And there's a nice mathematical property, too. The resulting posterior distributions remain concave.
Concave, meaning they curve inwards, like a bowl.
Sort of. The important thing is that it means they have a single peak, a single best solution. When the AI searches for the best set of parameters, it's always climbing a smooth hill to that single peak. It doesn't get stuck in local dips or confused by multiple equally good answers.
Okay, so optimization is easier.
Much easier and more reliable. It ensures that they can therefore be optimized efficiently using the gradient-based methods we mentioned earlier.
Wow.
So this combination of exact principles, clever approximations, and robust mathematical techniques like regularization ensures that Bayesian networks are not only smart, but also efficient, reliable, and interpretable in diverse AI applications. They provide a solid mathematical basis for reasoning under uncertainty.
So it's a sophisticated dance between exact mathematical principles and clever approximations, all designed to make these networks not just intelligent, but also efficient and reliable. That's exactly what we want in AI that operates in the real world, isn't it? It sounds like they're built to handle real-world messiness with precision, constantly balancing accuracy with practical utility. So, what does this all mean for us, the everyday person, or maybe for industries trying to leverage AI? Where do we see the tangible impact of this Bayesian thinking and these powerful networks in the world around us?
Right.
And how do they really make AI, as we said at the start, more robust, explainable, and mathematically grounded?
Well, the impact is profound, really. It extends to many areas where reasoning under uncertainty is absolutely paramount. And importantly, Bayesian networks aren't just for static situations.
Right, you mentioned dynamic problems earlier.
Exactly. They can also model things that change over time, which is critical for understanding dynamic processes.
Yeah.
Dynamic Bayesian networks, or DBNs,
DBNs, got it.
are an extension specifically designed for sequential data. They represent kth-order Markov processes, meaning the current state depends on a fixed number, k, of previous states over an extended set of state variables.
Okay, so they have memory of the recent past.
Precisely. This allows AI to understand and predict sequences, which is fundamental to many human activities, rather than just isolated events. Think of anything with a temporal progression: speech, video, financial data, patient monitoring, and DBNs become a powerful tool.
So DBNs are essential for anything that unfolds over time, like understanding spoken language, maybe tracking weather patterns, stock market fluctuations, or even the progression of a disease. That's incredibly broad.
It is very broad, yes. And a prime example of DBN's utility is in processing sequences like those found in language.
Ah, back to language.
Yep. Markov models of different orders are the standard representation of text sequences. This includes things like first-order Markov models, also called big-gram models.
Gigrims, 2 words.
Right. They define distributions based on P, WT, WT1. That's the probability of the current word given only the previous one.
Okay.
Then there are second-order Markov models or trigram models.
Trigrams, 3 words.
Using PWT1, WT2, accounting for 2 previous words.
So more content.
Exactly. These sequential probabilistic models are fundamental to how AI understands and generates language, including in tasks like speech recognition and machine translation. They allow AI to predict the next likely word or sound, making interactions smoother and more accurate.
So when my phone suggests the next word I'm typing, or a voice assistant understands my query despite background noise,
It's very likely leveraging principles from DBNs or similar sequential models built on these probabilistic ideas to make sense of that sequential data.
that's incredible. It really underpins so much of the natural language processing we take for granted today.
It really does.
But beyond language, how do these networks contribute to high-stakes decision-making where the consequences of error are severe and explainability becomes paramount, like, say, in medicine?
That's precisely where the robust and explainable nature of Bayesian thinking shines. The core strength lies in its ability to manage uncertainty in complex, real-world decisions. Now, while specific Bayesian network examples for medical diagnosis aren't explicitly detailed in all our sources, the principles are profoundly relevant.
The principles matter.
Absolutely. Consider medical screening, for example. The consequence of a misclassifying a tumor image as normal is obviously far more serious than the reverse error.
Hugely serious, yes.
This highlights the critical need for AI systems in these domains to be robust, explainable, and mathematically grounded. We need to trust them and understand why they make a recommendation.
Right. We can't have black boxes making life or death calls.
Exactly. And the sources mention that the AI and medical communities have learned their lesson from Watson, referring to some early overpromises about AI diagnosing rare diseases without maybe enough robust validation.
Ah, right. The hype versus reality check.
Kind of. And now they're focusing on more appropriate tasks for AI, such as drug and vaccine discovery, wearable devices, DNA sequencing, radiology, pathology, precision medicine, and doctor assistance.
More targeted assistive roles.
Often, yes. And Bayesian networks, with their causal interpretability and rigorous probabilistic framework, are a natural fit for such applications. They contribute significantly to the explainability and reliability demanded in health.
How so? How does the probability help a doctor?
Well, they allow AI to suggest diagnoses or interpretations with quantified uncertainty. So instead of just saying disease X, it might say there's an 85% probability of disease X given these symptoms and test results, and these are the key factors influencing that probability.
Ah, so it gives a confidence level and points to the evidence.
Precisely. That's much more transparent and useful information for a doctor making the final call rather than just a definitive yes or no.
That makes perfect sense. In medicine, probably cancer with a 90% certainty, along with an explanation of why it's 90% and what factors contributed, is far more useful and trustworthy for a doctor than a black box cancer classification.
Absolutely.
It allows human experts to integrate AI insights responsibly, retaining essential human oversight.
Exactly. And similarly, for risk analysis, the ability to model complex dependencies and quantify uncertainty is invaluable.
Risk, like in finance or engineering.
Or even autonomous systems, where there's financial risk, engineering safety, predicting outcomes in critical infrastructure like transportation, where self-driving vehicles need to make critical decisions in real time.
Yeah, big risks there.
The mathematically grounded nature and tractability gained through techniques like regularization make Bayesian networks a powerful framework. They help in understanding risk exposure and informing decisions where errors can have significant consequences.
Can you give an example, like for a self-driving car?
Sure. Imagine an autonomous vehicle. Understanding the probability of a pedestrian suddenly appearing from behind a parked van, given factors like traffic density, lighting conditions, maybe proximity to a school, the time of day,
Yeah.
that's a complex probabilistic inference problem.
Right. Lots of interacting factors.
BNs are exceptionally well suited for modeling that kind of scenario. They provide a transparent way to quantify and manage the risks involved, ensuring that the AI understands not just what is happening, but what could happen, and critically, how likely is it?
It sounds like Bayesian networks provide the fundamental framework for AI to grapple with what could go wrong and how likely is it, which is absolutely essential for deploying AI safely and effectively in critical areas.
I think that's a fair summary, yes.
They're about more than just making predictions. They're about understanding the implications of those predictions and the uncertainties surrounding them.
Exactly. And that brings us back to the broader significance. Ultimately, Collar and Friedman's work and the broader application of Bayesian thinking moved AI beyond purely rule-based systems or just statistical pattern matching. Those older approaches often lacked transparency and rigor and really struggled with real-world uncertainty.
So BNs provided a better foundation.
A much more robust framework, yes. 4. Robustness. By explicitly handling uncertainty, accounting for noise and missing data, and providing tools like regularization to create simpler, more stable models that don't overfit or give ambiguous answers.
Okay, robustness. What else?
Explainability. Through the graphical representation of dependencies and that potential for causal inference we talked about, allowing us to understand why an AI arrived at a conclusion rather than just what it concluded. That builds trust and allows for human interpretation.
Right. The why is crucial. And the third.
And finally, mathematical grounding. With rigorous probabilistic foundations and efficient inference algorithms ensuring the reliability and theoretical soundness of AI's reasoning, it makes its decisions auditable and trustworthy in a way that wasn't always possible before.
Robustness, explainability, mathematical grounding. Okay.
This powerful trilogy of benefits is what truly elevated AI's capabilities in the real world, allowing it to move from impressive feats of computation to something closer to genuine intelligence that can handle nuance.
So it's really about making AI not just capable of amazing things, but capable in a way that's transparent, trustworthy, and deeply intelligent, mimicking how we intuitively understand the world with all its inherent uncertainties, but with mathematical precision.
That's the goal, yeah.
That's a fundamental shift, moving AI from mere pattern prediction to a genuine understanding of the underlying processes and their probabilistic relationships.
Yeah.
What an incredible deep dive. We've journeyed from the foundational graph structures of nodes and edges all the way to the sophisticated algorithms like variable elimination and regularization that allow AI to map out and navigate uncertainty with such precision. It's clear that the work on Bayesian networks didn't just add a new tool to AI's toolkit, it really reshaped the very way we think about intelligent systems and how they interact with an unpredictable world,
It really did.
providing a level of transparency and rigor previously missing from many AI approaches.
The shift towards probabilistic graphical models fundamentally changed AI's ability to reason. It moved it closer to a human-like understanding of context, cause, and effect, at least in principle.
Right.
This means clearer insights, more dependable decisions, and a stronger foundation for the future of artificial intelligence. It allows for nuanced understanding in complex situations that simple if-then rules, or maybe even opaque deep learning models, could never quite capture in the same way.
Yeah, that transparency is key.
It's about building trust by revealing the probabilistic logic behind the AI's conclusions.
Absolutely. So the next time you encounter an AI making a complex decision, maybe it's recognizing speech, recommending a medical treatment, or even guiding a self-driving vehicle, consider this. How much of its confidence comes from simply predicting a pattern it's seen thousands of times, and how much from truly understanding the intricate web of if-then relationships, the hidden yet potentially transparent language of the Bayesian network?
That's a great question to ponder.
Constantly calculating and recalibrating the probabilities of its world, allowing for a more transparent and intelligent interaction. Think about the difference between just a guess, however educated, and a truly reasoned belief grounded in probability.